We're going to move on now and talk about our two methods using discounted cash flows. The first being the, we've got the net present value method and the internal rate of return method. And so we will look at those. When we talk about net present value, again, we're looking at the time value of money. If we invest $1 today and it's getting 12% interest, and it's being invested over 3 years, that's obviously going to be more than $1 that comes back to us after 3 years. And by the end of the third year, the investment will be $1.40.4. And why is that? Why isn't it just 12% a year times 3? And it's because the interest compounds. So every time we're paid interest, there's a little bit more money in that account that then earns interest. So we're earning interest on interest with compound interest. And so if we look at January, year 1, year 2, year 3, we are adding to the prior interest figure every time we pay ourselves interest, or multiplying by the amount that our new balance every time we pay interest. So we know that that dollar invested for 3 years at 12% comes out to $1.40 and fraction of a cent that we will get then on December 31st, 2018. How do we calculate backwards from that value that we're going to get of $1.40 and change on December 13th to the value of that dollar on January 1 when we made that investment? And the way that we're going to do that, and you can use financial calculators to do this, you can use Excel to do this, or you can use a present value table, which is what we're going to do now. So what the figures I'm about to show you will represent is the present value of $1. And so we want to look at the time period and the interest rate. So we've got 12% interest at 3 years. So the present value of $1 would be 0.712. Now, if we take the $1.40 and change and multiply that by the 0.712, guess what we get? That gets us back to the dollar that we invested back on year 1, January 1. Now, our last example was a single payout 3 years from now. How much would that dollar get us back? Well, what if we had a series of payments instead of just the one at the end? How would we then calculate that? Well, that's referred to as what's called an annuity, where we're going to have payments made annually, or it doesn't even have to be annually, it could be monthly, but some fixed payment over some regular period of time. And the present value, we could do this the really long and painful way of looking at each payment individually and then adding them all up, or we can look at them as a payment stream. So we'll look at both of those ways. So let's say we've got the present value of a $100 annuity for 5 periods at 12%. And so we could look at the present value table that we used on the first problem, and we could look at the 12% for each of those years, and that we would add all that together. And so let's just look. So we've got the present value year 1, year 2, year 3, year 4, year 5, and we add all those together, and that gets us the present value of the 5 $100 payment streams at $360.05 at 12%. But what we can do instead, because, doing all of these years, imagine if you had a loan that was like a 30-year mortgage. That would be really burdensome to have to do every year all by itself for the whole life of the loan. So we use instead what's called an annuity table. And it looks just like the present value table. And that's probably the thing that students who use tables as opposed to a financial calculator get jammed up most on, is they grab the wrong table. So notice this says present value of an annuity. And I'm just going to scroll back to the first table where this was just present value at $1. So make sure, and there's going to be another table we're going to look at again, make sure that you're grabbing the correct table when you're doing these calculations. So for the payment stream of the annuity, all we do is we go to our percentage, we go to the number of our payments, and there we are, 3.605. Now what we would do is we'd multiply that 3.605 times the payment, and that would get us to the same $360.50 that we got to using the individual method. And I just want to jump back to this. And if you remember, when we calculated each one of those years as discrete one-off payment periods, if we add all of those individual factors off of the present value table, it gets us the 5 payments off the annuity table. It gets us to the annuity factor of the 3.605. So using the annuity is just a quicker way of getting the calculations for a payment stream, which again, you could take individually one payment at a time and do this, but why do that when you can use the annuity table, which has all of that calculated in for. This net present value method is often referred to as a discounted cash flow method, and that's most likely how you will hear me refer to it, because that's what's most familiar to me. So how do we use this? Well, let's say that we have a project that we don't have the cash. A job comes in and there's a piece of equipment that we need in order to take on this project, and we're going to have to go borrow the money to do it. And the bank says, we'll lend you the money at 8% interest. And so do we take the project or not? Well, we need to know that not only are we going to recover the money that we spend investing in doing this project, but the 8% that we have to pay the bank. And if we don't recover at least the 8% that we pay the bank and the cost of the equipment, then we ought to reject the project because we're going to lose money by doing it. So in this example, we've got a cost of new equipment of $200,000, useful life of 5 years, and we want to get at least 10%. So maybe we had to borrow that $200,000 at 8%. Let's just say for the sake of argument, and we want to make sure that we get at least a 2% return. Or maybe it's costing us 10%, and we want to make sure that we get at least that back. And if we can't, then we shouldn't do it. These are the cash flows that we expect to get from this machine. Quite often with a machine, you're going to use it more in the earlier years than in the later years. So it's not unusual to have the higher cash flows in the earlier part of something's useful life. But notice that because these are uneven cash flows, we're not going to be able to use that annuity table, because that annuity table is premised on a consistent and even cash flow over the life of the project. So in fact, we are going to have to go year by year by year and calculate the present value of these one at a time. So we'll go to our present value table. We've got our time period here and our interest that we're trying to achieve of 10%, and here's what we get. So a present value factor at 10% year one of 9.09. We'll multiply that by the year one cash flow, and so on year 2, 3, 4, 5. We add up, these are our undiscounted cash flows, and this gets us our net present value of cash flows. And then we will subtract from that our initial investment of the $200,000. And so that tells us that if the answer to this was 0, remember this was all calculated at 10%. So that would tell us that we came in right smack dab at 10%. But in fact, this is a positive number. So that tells us that we're actually going to be earning more than 10% on this project. And that it exceeds 10%. If it was negative, then we didn't even make the 10%. And again, here is individually how we have calculated that series of cash flows. Again, subtracting out the initial $200,000 in investment to tell us that the net present value of this project is $2,900. And so because that is more than, that it gets us more than the minimum rate of return of 10%, then yeah, we're gonna wanna take a look at this project. So pros and cons of using this method. Well, it calculates in based on actual cash flows as opposed to income. It does certainly look at the time value of money, and we can use a present value index, which I'll get to in a second, to compare different projects. The disadvantage is that it's obviously more complicated because of the fact that we've got to, use the present value tables and do all that than the non-discounted methods. It also makes the assumption that we're going to, as the cash flows come back into us, that we're going to be reinvesting those, and we may or may not do that. Now we can get a present value index from this, and often we're looking at projects and we can't take them all. So we've got to compare the pros and cons of each of these projects because we want to make sure that we choose the one that's going to give us the biggest bang for our buck. And using the present value index is a way that we can compare those projects. So we get the total present value of the net cash flow and divide that by the amount to be invested. So using our last example, the $202,900 was the total value of the cash flows, which included our investment, and then we divide that by the investment, and that gets us a present value index of 1.0145. Now, if we've got multiple projects, we can take that present value index and we can compare it across multiple projects, and that tells us basically from a discounted cash flow basis which would be the most desirable. Anything with a positive net present value is obviously going to be better. Where the net present value was negative, meaning that it came in below our hurdle rate, you're going to have a present value index of less than 1. So if I go back here, we've got 0.96 on project proposal C, and again, totally not related to the example we just did. These are entirely 3 different projects, but this suggests that we did not come in above our hurdle rate. And so proposal B is going to return us $1.08 present value per dollar invested, whereas proposal A only gets us $1.07. And we would actually yeah, and let's see, I should look. We actually, proposal B requires a smaller initial investment than proposal A does. So not only do we do better in the end for it, we have to lay out less cash in order to do it. And so moving on, do I want to move on? I'm going to actually end this video here, and we're going to go on to the internal rate of return on the next video.